It's our pleasure this evening to have with us Dr. Daniel McIntosh from the Department of Physics and Astronomy. Dan got his bachelor's degree from a fine institution, UCLA, and a PhD from a very good astronomy department at the University of Arizona. He is currently Distinguished Associate Professor and he is serving as the chair of the Department of Physics as well. His research interests are in the area of galactic evolution, if we can use that word, being this close to Kansas. And he has also been the recipient of a number of awards. 2016, he was selected as a Presidential Teaching Award winner for innovative teaching. 2017, he received an award from the College of Arts and Sciences, the Norman Royal Professorship, and in 2018 was selected as a Provost Fellow. The talk tonight, although we call this annual dinner, refer to it as Starry Night, we will be staying a little bit closer to home. And Dan will take us on a tour that began just over 40 years ago when the first Voyager and the second Voyager missions launched. And it was timed at the 1977 era to coincide with a very fortuitous alignment of the giant planets, Jupiter, Saturn, Uranus, and Neptune. And they have since passed by, and a number of other missions have followed, exploring our own solar system in much greater detail. So with that introduction, let me turn it over to Dan to give us a unique tour of the many worlds of our solar system. Dan?
Charlie, thanks so much, and thank you all for attending tonight. I really enjoy giving these kind of talks, and so a quick outline. I'll spend a little more than 5 minutes on a brief introduction to set the stage, and then the bulk of the talk will be on our unique tour of the many worlds of the solar system, and then we'll conclude with some closing thoughts. I just want to say that I am happy to entertain questions during and after for as long as you like. That's actually one of the most fun things about doing these talks, though I won't be able to monitor the chat window and give the talk at the same time. So if somebody has a very burning question and wants to interrupt, feel free just to interject, or Jacob can interject as well. So here we go. So everyone can see the transition change to the next slide? Thumbs up. I want to make sure. Okay, I got a thumbs up. Awesome. All right, so a little bit of historical context. A few years ago marked the end of an era, a great era of space exploration, with the end of NASA's Cassini mission, which was a long mission that spent 14 years almost orbiting Saturn and studying all of its moons and its ring system. And at that same time, we marked the 40th anniversary of this once-in-a-lifetime alignment that Charlie had spoken about, in which NASA scientists and engineers realized that the outer four planets were lined up in such a way that only happens every few hundred years, that we could launch two missions, the Voyager 1 and Voyager 2, and explore the outer solar system for the first time in this grand tour. And so the launch of these missions really ushered in a new era that improved vastly our understanding of the variety of worlds in the solar system in greater and greater detail. Now, to put this in perspective, just 20 years before the launch of the Voyager mission, our understanding of the solar system was very limited. We had very incomplete data. For instance, at the time, we only knew that Saturn had a handful of moons. This is a poster from 1959. We now know that Saturn has at least 82 satellites orbiting it. And our information at that time was also often quite inaccurate. For instance, this picture of what we imagine the largest asteroid Ceres to look like is nothing like it actually looks like, as we see in this picture from NASA from about 5 years ago. So the dawn of the space age began by a combination of hope and fear in America about new technologies that came out of post-World War II during the atomic age. And this hope and fear led to a time of great teamwork and investment in federal investment in research and technology for the exploration of space. And this is nicely, this teamwork and this investment is nicely demonstrated by the founding of NASA in 1958. Now that, with NASA began America's really dominance of space exploration and solar system exploration for the next more than 50 years. And I'm going to briefly highlight this dominance with this graphic, in which I'm going to go chronologically through the firsts in terms of solar system exploration, in terms of orbits around major planets and objects in the solar system, flybys, and landings. Now, of course, the space race and the space age began with the Soviets' launch of Sputnik in 1957, and that began the race to the moon, which the Soviets had a lot of the first flyby of the moon, first landing of the moon, and that also ushered in the beginning of the exploration of the inner solar system during the 1960s. In the 1970s, we became more sophisticated with our exploration of the inner solar system, and we started to expand our reach to the outer, at least Jupiter and Saturn, towards moving out of the solar system towards the edge of the solar system. And the 80s saw the beginning of fewer missions, but much more expensive missions that extended all the way out to Neptune and beyond, and also started accomplishing much more serious exploration of the inner solar system as well. And so what we see here is the US dominating the first landings, the first flybys, and the first orbits of most of the major planets in the solar system. Now, as an educator and a scientist and a citizen, I've long reflected on the legacies of space exploration, and in particular of the exploration of the solar system. And I've reflected on the debate over the cost versus benefit of federally funded investment in this kind of exploration. And I've reflected on what is at stake depending on what we choose to do moving forward in terms of this exploration. I believe that, if not the greatest, definitely one of the greatest legacies of space exploration was inspiring interest in science. And across the world, millions of people, like myself, were personally inspired by Voyager's mission and Voyager's new detailed and color images of the grand gas giants of Jupiter and Saturn and beyond, and of their myriad collection of worlds, of moons, which are worlds in themselves. And so tonight I'm going to take us on a unique tour of the many worlds in the solar system. And by what I mean by worlds are objects that are large enough that gravity will shape them into roughly a round sphere shape. So unlike how we usually think of the solar system, we have our 8 major planets. There are many, many dozens of objects that fit this definition. And I'm talking about worlds that have atmospheres and clouds and weather, worlds that have mountain ranges and valleys and canyons and plains, and even some worlds that have vast ocean systems. So rather than a kind of typical tour that you might see when we think about space exploration, where we start with the inner planets and work our way outwards and just consider the 8 major planets that we're familiar with, I'm going to do a different kind of tour where I consider the worlds in order of their size from the largest worlds to the smallest. And I'm going to explore the few dozen of the largest worlds as we go. And a fun fact that I like to tell my astronomy students when thinking about the solar system and all of these planets and all of these worlds and the billions of comets and the millions and billions of asteroids is that all of this stuff is actually just the leftover scraps from the formation of the sun about 4.5 billion years ago. And the sun really dominates in terms of the material, the mass, how much all the stuff weighs when combined. The sun is basically everything. All these worlds are just the leftover scraps, but they have a really amazing variety. And of course, one of them that's very important is our own world, Earth. So sit back, relax, and prepare for departure. During our journey, we will think about we'll see how our understanding of our local system of worlds, the solar system, has greatly expanded in just the last 40 years, starting really with the Voyager missions, the 2 Voyager spacecraft, the Voyager mission. And along the way, we will consider some of the most exciting and unanswered questions that are within our grasp to answer with the technology that we have today. Now, as we start to arrive at our first destination, of course, Jupiter is the largest world in the solar system. I want you to take a look at your flight monitor at the top of your screen. And all of our destinations are going to include the same kind of information. So I'm going to take a moment here to walk us through our flight monitor. On the left-hand side, we're going to name the world that we're visiting, and we're going to give some key facts about the atmosphere and the composition. Does it have a moon system? And does it have any rings? We will also have this little diagram that represents how the planet is spinning on its axis. On the right-hand side, this little sphere is going to represent a relative size of the planet compared to, or the world compared to the previous larger world, as you'll see in a second. It's going to give the ranking of the world in terms of its size. Jupiter is the #1 largest world, and it's going to give its size in kilometers. Who cares about that? More importantly, relative to the Earth. And so Jupiter is a little more than 10 times the diameter of Earth, but relative to the largest object in the solar system, which is the sun, it would be the size of the little sphere in the upper right-hand corner compared to the sun size, which is this large yellow circle, the sun being a little more than 100 Earths across compared to Jupiter. And finally, at each destination, we'll include some fun facts. I'll talk about some of them. Some of them I'll just leave up to post for you to consider as I'm going through the slideshow. And I will take some time and give a couple highlights of some of the key details that are featured in our flight monitor. So the first fun fact about Jupiter, Galileo discovered this giant swirling storm, the Great Red Spot. We now know, and we have videos, I recommend going to YouTube and watching videos from the Voyager spacecraft of this system swirling and turning like a giant hurricane. It's a hurricane that's more than an Earth in diameter across. So it's a monster storm, and it's lasted at least 400 years since Galileo discovered it. Now, we now know that Jupiter has a ring system, and this is because of Voyager. Voyager actually took the first pictures of the ring system, as we can see in this picture. We did not know that Jupiter had a ring system. Its composition, I won't go into much detail on the planets in terms of composition, but just for Jupiter to set the stage, it's actually a very big light object. It has a rocky kind of metallic core, kind of like a small planet at its center with a lot of ice moving out, and then it has a very, very thick atmosphere, an atmosphere that's about 2 Earths diameter in terms of how deep the atmosphere is before it gets down to the icy part or the slushy. It's kind of like a slushy down there in that metallic hydrogen part of the planet. And here we have this beautiful picture of the cloud tops taken by a more recent NASA mission. Jupiter has a vast moon system. Here's a fun picture that if we had a city on Io, this is what Jupiter would look like in our sky because Io is so close to Jupiter's surface. Now, with respect to Voyager, why Voyager is so important, before Voyager, which is only 40 years ago or so, we knew of only about a dozen moons around Jupiter. Now we know of almost 80. And Jupiter is a little bit weird because it has 4 very large moons that, of course, Galileo discovered, Io being one of them. And we'll get to the other large moons in a moment because they're worlds in themselves. But those 4 worlds, of course, are important because Galileo could observe in his little tiny telescope Jupiter, just like we can see at the Varco telescope here on campus. And you could see the 4 biggest moons. It's just, they look like little tiny stars lined up in the diameter, like along the equator of the planet. And if you watch even over a couple of hours, you can literally see those stars or those moons moving because they're orbiting Jupiter. It was one of the key observations that Galileo had to understand that the Earth was not at the center of the solar system, that lots of objects orbit other objects. Now, besides those 4 large moons, Jupiter has a whole host of tiny moons. The 5th largest one, being this Alma Thea, is tiny. It's only about 60 miles across. And these are actual pictures from Galileo. Phoebe, for instance, on the left, was one of the first of many moons that Voyager discovered on its flyby. And what you can see in these pictures is that even very tiny objects, when we're flying a spacecraft by, we can actually get some very interesting information about these objects that we can never get from Earth, even with our greatest telescopes, such as the Hubble Space Telescope. One quick aside, most of the moons of the outer planets are basically like comets, rocky and icy, except for some of the larger moons, they have iron cores, kind of like the inner planets. So now if we move on to Saturn, Saturn is quite like Jupiter in most respects, except of course for its beautiful and vast ring system. It's nearly the same size. So you can see the upper right-hand corner, the larger outline is the size of Jupiter's diameter compared to Saturn, which is the yellow circle. So Saturn's only about 9 Earths across instead of a little more than 10. So it's nearly the same size as Jupiter. It has the same composition. It's basically the same kind of a very light gas, low density planet. Some astronomers say it's so light that it would float on water if there was an ocean big enough to set the planet on top of water. It has a huge collection of moons, just like Jupiter, and of course its giant ring system. Here's an artist's conception of what we know the ring system to be. The ring system is actually a collection of literally billions of particles. Some are small little grains of sand, all the way up to boulders the size of houses. And they're all going around the planet in the same plane, all in the same direction. So in a way, you can think of the particles that make up the ring system as billions of little tiny moons orbiting Saturn, but they're different because of the collection compared to the regular moons. Here's an actual picture from Cassini of the ring system completely edge on, and you can see there's 2 moons shown here, that the moons orbit exactly in that same plane as the rings, and they also all orbit in the same direction. So if you're looking down on the North Pole of Saturn, all the planets and all the rings, all the moons and all the rings are going around Saturn in a counterclockwise direction, which is an interesting clue to how they formed. One of the smaller moons of Saturn, which is a highlight, one that I like, it turns out to be the 96th largest world in the solar system. And I like it because of its giant crater, which was caused by an impact long ago that was almost violent enough to break this little moon into pieces, but it didn't. And it just has a coincidental shape, so something from our sci-fi movies. One of the larger moons that Voyager discovered is this one called Prometheus. And we realized from Cassini recently that it orbits in this funny way around one of the outer rings of Saturn, and it's kind of wobbling as it orbits around. And so it causes waves to be created in the rings, this one outer ring of Saturn. And the Voyager missions had discovered this weird ring. They said the ring was kinked or braided, and astronomers and scientists for a long time couldn't figure out why that was true. It took about 30 years. It took the Cassini mission for us to finally figure out what was going on. And it's this interaction between this little tumbling moon and the ring system. One of my favorites is a little tiny moon called Pan that sits in a gap in the ring system. And because Cassini spent so much time orbiting Saturn, unlike Voyager, which just flew past Saturn very quickly, it could actually, the scientists and engineers programmed the Cassini mission to go take a very close look at Pan, and this is what they discovered. And so Pan turns out to be this weird ravioli-shaped moon. And why it has a ravioli shape, why it has this weird edge to it, like the edge of a ravioli, is because it's actually taking material from the ring on either side of it, and gravity is pulling that material onto the moon, and it's collecting on there to build this equatorial weird fan, whatever you want to call it. And so over time, Pan will get larger, and the gap between the rings that Pan sits in will get larger because it's taking material through gravity as it orbits around. probably the most important discovery of the Cassini mission in making Enceladus, which is not a very large moon, but a very important moon at the 69th largest world in the solar system, is this tiny little icy moon. Here's a beautiful up close picture of it. What's so important is that we have realized that there is a salty subsurface ocean underneath this icy crust. So the right-hand side is a real picture, and you can see these big cracks and grooves in the surface. There's material coming, water, salt water coming through the cracks and going out into space. And so the scientists at NASA sent the Cassini probe really close to that moon and threw the material coming out of the cracks so they could basically taste that material and show that it was not just water ice, but water ice with salt. And that means that the water is on top of a rocky surface, just like we have in oceans on Earth. And that means lots of minerals are in that water. So it's possible that this would be a good place to go look for life. Now, moving from the two gas giants to Uranus, we basically have twin, what are called ice giants. So Uranus is about 1/2 the diameter of Saturn, as you can see in the upper right-hand corner. It has a very smooth atmosphere, so it's pretty featureless. A kind of interesting fact about Uranus is that it's knocked over on its side. So it literally rotates on its side. So one pole is always pointed towards the sun and one pole is always pointed away from the sun all the time. It's slightly different in composition than Saturn and Jupiter. Mainly it's a lot more ice and it has a less thick atmosphere. That's as much as I'll say about its composition. Just like with Jupiter, the Voyager missions discovered that there is a small and very hard to see ring system around Uranus. There's also one around Neptune. And so all the large outer planets have big moon systems and big ring systems. And as with the outer giant planets, it wasn't until Voyager, the Voyager mission, that we actually started to understand just how big of a moon system that Uranus has. Before the Voyager mission 40 years ago, we only knew of 5 moons orbiting Uranus from our best telescopic observations. We now know of 27 and counting. This is 2 pretty pictures of moons. These are small objects in terms of size of objects or worlds in the solar system. But Miranda over here on the right, you can see like on the upper part of it, it looks kind of like a normal moon surface with craters and mountains. And in the bottom part, it looks all distorted as if the object was somehow taken apart and put back together, which is exactly what the scientists think happened. So unlike the previous moon I showed around Saturn that got hit, but not hit hard enough to break apart, this object was smashed, broken into pieces, and as it orbited around Uranus, it probably made a very beautiful ring system for a while. And then over time, gravity brought all those pieces back together to reform this moon into a big sphere, but it looks very malformed. So this probably didn't happen that long ago in terms of solar system age. What I mean, probably tens or hundreds of millions of years ago, but that's not very long compared to the age of the solar system. And then this little tiny moon on the left, Puck, this is just, again, to give you an example. This is one of the 10 larger moons, one of the 10 moons that Voyager discovered around Uranus. And this is its only picture as Voyager goes flying by very quickly at about 50,000 miles an hour. And it takes a snapshot of this tiny little moon. We can never see this from Earth or even with the Hubble Space Telescope. And flying by, even at that great speed, we can actually collect a picture, an image, if we're lucky to be going by on the side that the moon is, and see some of the details of this tiny little world. Neptune is essentially Uranus's twin. It only in the upper right-hand corner. It's made of the same material. It has this weird storm, kind of like the Great Red Spot on Jupiter in its atmosphere, which Voyager discovered. It also has a very, very hard to see, faint ring system. And here's a picture from Voyager 2, which has discovered the ring system. And also, like the other planets, there was only 3 known moons before Voyager, and the Voyager missions discovered 5, and then since then we discovered some more. So here's an example of a little tiny moon, Proteus. You can see a picture from Voyager compared to our best image of the the Neptune system from the Hubble Space Telescope. Basically, Proteus just looks like a little tiny dot, a little star orbiting the planet. If we monitor over time, we can see that it's going around Neptune, so it's not a star, it's a planet, but only if we go out there and visit and do exploration with our robots and our spacecraft, can we actually see these planets as the worlds that they are. So now I'm going to move to the inner part of the solar system, to the largest of the rocky inner planets, of course, our home. Our home is about 1/4 the diameter of Neptune and Uranus. And a kind of way to think about it is if you compare Earth to Uranus and Neptune, it's the same as if you compare the moon to the Earth. The moon is about 1/4 the size of Earth. And so the Earth is fairly big, but nothing like these ice giants. Here's a beautiful picture, the first ever picture taken by humans of the Earth and the moon in the same exact picture. And this was taken by Voyager 1 right after its launch, as it's leaving the Earth system, the Earth Moon system. And the composition, lots of rock and metal, iron in the core. That's basically all we need to know about the inner planets. And a very, very thin atmosphere, of course, that protects us and causes conditions for life here on Earth. It's only about 10 miles really thick from the edge of the surface of the Earth to the outer part of the atmosphere. Venus is Earth's sister, nearly exactly the same size, same composition. The real big difference between Venus and Earth is it also has a thin atmosphere, but there's a whole lot more material in the atmosphere. So the atmospheric pressure is incredibly strong. And there was a runaway greenhouse effect in its past. And so the surface temperature of Venus now is something like 800 degrees Fahrenheit, hot enough to melt lead. So it's a very inhospitable world, even though recently in the news we heard that there might be some evidence of some sort of indication for very small microscopic life in the upper atmosphere, but that remains to be seen. Another fun fact about Venus is it spins backwards, or in other words, it's upside down, which means it was probably hit very violently in the early formation of the solar system and flipped on its head. We can see what its surface looks like with radar imaging, such as the NASA Magellan mission. So lots of craters and mountains and volcanoes and plains and etc. And here's a pretty cool picture. The Soviets have landed several probes on the surface of Venus. So this is a picture of the actual surface of Venus. Looks like a very inhospitable sort of desert place. Because the pressure and the temperature are so bad and so high on the surface of Venus, these Soviet spacecraft, these probes, lasted only for a few hours before they died. Now we're moving to the second to the largest of the seventh of the largest worlds in the solar system, which is Mars. Mars is about half the diameter of Venus and Earth. It has a very similar composition. What's cool about Mars is that it's been so well studied because we've sent so many space probes to orbit and take pictures of the surface and landing rovers on the surface to explore around. From those missions, we discovered things like the fact that Mars has the largest volcano in the solar system. Olympus Mons right here is something like 5 Mount Everests tall and about the size of Arizona. It has some giant canyon system, which you can see in this picture right here, which dwarfs the Grand Canyon on Earth. Over to the left, you can see 3 round circles that are kind of brownish color. Those are the big volcanoes, the biggest one being kind of at 9 o'clock, which is this picture I'm showing right here. Mars does have a couple moons, but they're not the kind of moons like our moon. They're basically captured asteroids. And so if you look at them, here are real pictures of Phobos and Deimos. Phobos is only, that's about 13 miles across. So it's a very tiny, tiny object compared. I wouldn't call these worlds. This is basically caught a little rock in orbit around Mars. But Mars, we have all this activity that's been going on. The first mission that landed a probe on the surface of Mars was the Viking mission, and that was in the mid-1970s. So we've been there for a long time, humans have, studying the surface in great detail. Right now, there's 3 orbiters and 2 rovers at work there. Here's some pictures from the surface of Mars, more pictures from Curiosity, a portrait here and a picture of a sunset from Mars. And then what I really love, you can see all these beautiful images, especially from the Mars Reconnaissance Orbiter. These are just exquisite images of all kinds of variety on the surface of the planet from outer space. So we're in orbit around Mars and we're taking pictures, and you can see sand dunes around a crater. There's weather on the surface of Mars. There's dust devils and clouds and dust storms. You can see these ice sheets. You can see these weird stripes, which are sand dunes blown around by wind to make these stripy features in the lower right-hand corner. And a really interesting thing that we've learned in the last 5 or so years about Mars is that in its first billion years or so, there was a giant surface ocean of liquid water. And so the conditions on Mars were definitely ripe for life in its first billion years or so. This is a 400-foot sort of cliff where they've used some false color, but basically what we're seeing is water ice just underneath the surface. And the surface of Mars now is pretty inhospitable, though there are a couple times places on the surface that get to be slightly above freezing. And so there is evidence for liquid water percolating out of the soil sometimes on the surface of Mars. And so there's lots of talk about going to Mars and looking for life or evidence of past life in the near future. All right, now we're going to move away from the inner planets. We so far focused on 7 of the 8 major planets, the ones that are familiar to us with Mars. And when we talk about compared to Mars, we're going to start talking about the larger moons of some of the outer planets. And you can see compared to Mars, Ganymede is a world in itself. It's nearly the same size as Mars, as shown in the upper right-hand corner. The picture here, of course, is Jupiter with Ganymede peeking out from down below. But let's take a zoom in to look at its surface. It's actually a pretty smooth surface with lots of craters. And the Voyager scientists realized early on that most of Jupiter's large moons probably have a liquid ocean underneath an icy surface. And so now there's lots of reason to look at all 3 of the the larger moons of Jupiter and to believe that we have conditions for life like we saw with Enceladus. Titan is the largest moon of Saturn. It's nearly exactly the same size as Ganymede. Yep, Ganymede. Make sure I'm remembering right. But much different. Its composition is different, but it has an atmosphere, it has weather, and it has liquid oceans and lakes, except the liquid is not water, it's methane. It's so cold on the surface that methane is turned into a liquid, and you can literally see the reflection of the sunlight, the distant sun reflecting off the lake back to the camera on the Cassini mission shown here. And I love this sequence of pictures. These are actual real pictures. The Cassini mission had a probe on it called the Huygens probe that was detached from the spacecraft and was going by Cassini, and it went and landed on the surface to see what was going on. And so these are pictures as this probe is coming through the atmosphere and heading down to the surface. And what we have on the right is the surface of a distant world, the most distant world that humans have ever taken a picture from the surface, which is a pretty neat thing. That was 15 years ago. Mercury is the last of the major planets, but smaller than some of those big moons. It's also much different than them. It's very, very dense, mostly rock and metal. We can see that it has a very huge iron core. That's because it's so close to the sun. So it's mostly molten, very hot, very inhospitable. These are recent pictures from a NASA messenger mission that went and orbited Mercury to get a lot of detailed images. No rings, no moons. I like to think of it as a planet or a world that's about the size of the moon, but in a very dangerous orbit so close to the sun. Nearly the same size as Mercury is one of Jupiter's large moons, Callisto. Again, we can see a very smooth surface, which is because it's an icy surface. And when impacts that would normally cause craters hit, if they're big enough, they break through the ice and then the ice refreezes. And so we see these ripples coming out of the surface, this kind of ring pattern, which represents the ripples as the ice refroze. So it too has a subsurface ocean, and we do believe that it's salty, like in Enceladus and in Ganymede. Io is the one oddball of the 4 big Jupiter moons, a little bit smaller than Callisto, but very close to Jupiter. It has a lot of metals and rock, And what Voyager discovered as it was going by Jupiter, the Voyager mission, it discovered that Io is one place in the solar system besides Earth that has active volcanoes. And this came as a big surprise to the NASA scientists back in the 1980s. You can see this picture from a more recent NASA mission flying by Jupiter to use Jupiter's gravitational force to slingshot it out on its way to Pluto. And you can see literally the plume of gas from that volcano, and you can see the volcano glowing. So this is the kind of volcanoes we have on Earth with liquid lava, basically liquid hot rocks. Here's a close-up picture of Io. The orange circles are from sulfur coming out of these volcanoes and spewing out all over the ground, all over the place. And this material gets up into the atmosphere of Io, makes a little bit of an atmosphere. And then Jupiter has these huge magnetic fields that draw some of that material into the poles and cause these weird kind of auroras at the pole of Jupiter. And this is caused, scientists believe, from the material that Io is producing from its volcanoes. All right, now the moon is the 13th largest world in the solar system, basically the same size as the big moons of Jupiter as we just saw. A fun fact, 24 astronauts of the Apollo mission, which we just celebrated the 50th anniversary of the landing on the moon, 24 astronauts went to the moon, only 12 landed on the moon. And I saw a really fascinating talk recently with Edgar Mitchell at Linda Hall Library. If you haven't seen this movie, I really recommend this movie. It's on Netflix. It's called The Last Man on the Moon. And it's all about Eugene Cernan, who was the last man on the moon, seen here driving the little moonmobile from Apollo, I think 15 is the number. We should all know all these people's names, I feel like, and actually I'm embarrassed I don't know all their names. All right, some more worlds that are moons. So Europa is another one of Jupiter's big moons, about the same size as our moon. Again, lots of cracks on the surface, very smooth, icy surface, which reveals that there's another ocean underneath that surface as well. And most scientists think that this is probably, if we want to pick one of these moons to go to, one of these worlds that has an under ice liquid water ocean, Europa is the one that everybody's banking on as the best place in the solar system to look for life that exists right now. And so hopefully in the future, we'll have missions to Europa. Now I'm switching gears. We're at the 15th world and getting close to the end of our tour. This is the largest moon of Neptune, the largest moon of any of the two outer ice giants, and nearly the same size as the big moons around Saturn and Jupiter. But this moon is interesting in particular in a certain couple of ways. So Triton here, probably the most interesting thing is its orbit and its size compared to all the other moons of Neptune is much, much larger. It is a world in itself. And as you can see in this diagram, you have all these small moons going counterclockwise around Neptune in pretty much circular orbits, and yet Triton is going backwards and in a very elliptical orbit. And because of that, and because of what it's made out of, as you'll see in a minute, Triton basically is Pluto's twin. Scientists believe that Triton was captured, was actually something that are called trans-Neptunian, objects that are beyond the orbit of Neptune, and some of them are quite big. This would be the biggest one, got too close to Neptune, and with Neptune's large size and great gravity, it pulled that object into this weird orbit. So basically captured this outer solar system object and put it into orbit as a world around it. But Triton had some really interesting surprises that the Voyager 2 mission revealed. You can see here in close-up pictures from the surface, from Voyager, what are called ice volcanoes. And so you see all these little smears, like the little dark smears, all kind of going in the same direction on the surface. I've pointed out 3 with arrows here. This is caused by material in the inner parts of this icy moon. As it gets really close to Neptune in its elliptical orbit, it gets squished by tidal forces and kind of heats up the inner material, and it causes it to squeeze out in places to cause these little ice volcanoes. And they're all over the surface of the planet. And so that was another big surprise that the Voyager mission discovered. And these are the only images that we've ever taken from the surface of, not from, but of the surface of Triton, because we sent no other missions to Uranus and Neptune, only Voyager 2. Now, Pluto, basically the same as Triton, but in orbit around the sun, not in orbit around a major planet. This is what we thought Pluto would look like, with the sun in the very great distance and this large moon called Charon, which I'll talk about in a second. Because of Pluto, and as you'll see in a minute, some other objects just like Pluto, we had to come up with a new category for objects like Pluto. And so Pluto was demoted as a normal major planet. And you can see it's the 16th largest object in the solar system. It's smaller than our own moon. It's not much of a planet, but it is something called a dwarf planet. And so it's the largest known dwarf planets. Triton would have been the largest, but it got captured by Neptune. NASA sent the Horizons mission, New Horizons, and finally, after a 10-year voyage, went flying past Pluto. And so here are gorgeous, beautiful images of the surface of Pluto. This is an actual video made from images of that spacecraft. And so we can see Pluto in the center, and we can see its main moon, Charon, is so large that it actually causes Pluto to wobble in space as it's orbiting the sun. And so we see Charon orbiting Pluto, and basically Charon is so big that the center of mass for that system that's in orbit around each other is outside of the surface of Pluto. And here's a family portrait of a couple of its other moons, Charon being the 25th largest world of the solar system. We'll come back to that in a minute. Then there's a bunch of little tiny objects around Pluto as well. And then finally, again, basically the same as Triton and the same as Pluto is this object called Eris. And this is the best picture we have of Eris because it's so far away. It was just discovered 15 years ago using telescopes here on Earth, and really looking hard at the data for little tiny specks of light, as we see in this picture from the Hubble Space Telescope. It's so far away and so small that even with Hubble Space Telescope, it just looks like a point of light because it's so distant. It's basically twice as far away as Pluto is right now from us. Hopefully someday we'll go to visit it. What we can see though is it does have a little moon, Dysnomia, which is the 41st largest world in the solar system that we've cataloged so far. But the fun fact really about Eris is its discovery in 2005 really caused a big debate in the astronomy community about how do we classify these objects? Because if we start discovering more and more objects just like Pluto, about the same size as Pluto, are we going to have 10, 11, 20, 30 planets, or do we have to categorize them as something different? And so finally, after a lot of debate, we all agreed to demote Pluto and call objects like Pluto and Eris dwarf planets. And the vast majority of them sit out there past the orbit of Neptune. Just a couple more. Number 18, we don't have any pictures other than we know that it's there. So this is an artist's conception of an object that should be round, but it spins so fast, it's kind of stretched out. And then another one, I skipped number 19, we'll come back to that in a minute. The third largest dwarf planet just got named recently, Gong here. And again, basically the same composition, same material, same characteristics as the other dwarf planets like Eris and Pluto. And so at this point, we have quite an inventory of these dwarf planets. Here are some of the largest. I'm just popping up numbers. These numbers represent where do they rank in terms of the sizes of worlds in our solar system. You can see they make up a portion of the top 30 largest worlds. Now I'm going to rush through the last 9. So we have an even 30. These are basically all moons of the outer planets, Uranus, Saturn, and Jupiter. I'm not going to spend a lot of time talking about them. I'm just going to show the pretty pictures. Most of them, the pictures are from Voyager 2, as we can see right here for Titania, which is one of Uranus's moons. The main thing to look at is the pretty pictures, and then notice again the comparison to the last object. This object is a little bit smaller than, say, Eris and Pluto, sorry, which are shown as the pink circle. So we got Titania, which is at Uranus. We got this moon Rhea at Saturn, number 21. Here's a nice close-up picture of Rhea from Cassini, a really close-up picture. Number 22 is another one of Uranus's moons, Oberon. This is a Voyager 2 picture. That's the only picture there's going to be because only Voyager 2 went to Uranus and Neptune. It has some huge mountain on it. That's kind of fun. Another one of Saturn's moons, Iapetus, has this great equatorial ridge that's as tall as Mount Everest. We can see in this picture right here. Number 25, we already talked about this. This is Pluto's biggest moon. Uranus's moon Umbriel and Uranus's moon Ariel. So again, Hubble Space Telescope, our greatest technology in the last 20 years, taking the best picture we could possibly take from Earth orbit. And you can see Ariel is just this little speck of light on top of the disk of Uranus. And here's the picture from Voyager as it flew by. You can see plains and craters and all kinds of canyons. Dione at Saturn, it's a Cassini picture. Here's a Voyager 1 picture, another Cassini picture. Tethys is another one of Saturn's moons. You can tell all these moons are basically the same size. They're about 15 to 10% the diameter of the Earth. So smaller than our own moon, but little worlds in their own right. Here's Tethys quite near the ring system. And here are some close-up pictures. These are really gorgeous pictures. So you can see another object. This is again Tethys, and this is a close-up of Cassini. It got hit. It has this huge impact crater on it. And it also has this giant kind of canyon system that goes all the way around. So they think also that this planet was broken apart at one point in time and then melded back together by gravity. All right. So as we near the end of our tour, it's worthwhile, as we're passing back through Saturn on the way home, to consider the immortal words of Carl Sagan, that the Earth is a very, very small stage in a vast cosmic arena. This is a picture that Cassini took that replicated what Sagan had the Voyager 1 mission do as it left past Saturn on its way out of the solar system, as it departed and Voyager 2 went off to Uranus and Neptune. So nearly 1 billion miles away, you can see Earth as this little speck. This is the picture that Carl Sagan had taken from Voyager 1 back in the 1970s. And he called Earth a mote of dust suspended in a sunbeam. I love that. So one more stop on the way, very quickly. The largest dwarf planet in the inner solar system is Ceres, shown right here. And here's some really beautiful close-up pictures of its surface from the NASA Dawn mission 5 years ago. Okay, so now stow your tray tables, and as we head on home, it's worth spending a couple minutes thinking about and considering the question about how much have we spent to do all this space exploration. And so for that, I like to show these couple slides that I often show my students. On the right-hand side, we're showing the amount of dollars in billions of dollars that NASA has cost over its whole lifetime of this program. You can see the peak during the Apollo mission in the mid to late 60s. Most of the NASA budget was spent on the Apollo program to land men on the moon. At that time, the budget increased a little more than 2 times. But in relative dollars, how much are we talking about? I'll show in a second. It's worth, though, to put this amount of money that we're spending in perspective, because it's actually a very tiny fraction of the amount of money that we spend as a country on all of the different spending. And just to put it into context or into perspective, I love to show this cartoon and this fact, which is if you consider the entire history of NASA from its founding in 1958 until 2017, its entire budget in adjusted dollars was equivalent to the 2009 bank bailout. Now, of course, that was important, but I'm just giving it perspective that when we choose to spend money, we choose to spend money, and all this exploration that's happened with NASA and the great points that George Will is bringing up here about what NASA has done for us, I think are worth considering over that over 50-year lifetime of NASA, nearly 6 years. In terms of people cost, this is a good, so I like to use these public talks for helping people understand in a relative sense how much we spend on space, and not just on space, but in science in general. And so this graph shows the amount of tax dollars that are spent on basic research and development as a percentage of the federal budget. And for the last, 40 years, it's basically been around 2%. So in other words, for every dollar you give Uncle Sam, 2 pennies goes to basic research and development. And actually one of those pennies goes to the NIH, the National Institutes of Health. The rest, the other penny, goes to all the other federally funded scientific research and development agencies, NASA being about a half a penny. In terms of human dollars, like the average taxpayer spends about $40 in their taxes each year, or about six packs of beer on all of this research and development. That's it. NASA being at about a half a penny is equivalent to about every man, woman, and child going to the movies 1 time a year. That's the cost to do all the cool stuff and the important stuff that NASA is doing. And the return on investment for this small amount of money is huge. NASA boosts the economy in all 50 states, and NASA hires thousands of highly skilled and hardworking Americans. And so I like to end my talk with a simple consideration. If we just thought about doubling our investment in NASA alone, and I would make the same argument for all the federally funded research and development, but just change our investment in NASA from less than a half a penny to just a penny, we could do all of the amazing things that NASA scientists and engineers have thought about, like going and looking for life in Europa's oceans, looking for life, potentially weird kinds of life in the oceans on Titan, putting huge telescopes in space, much, much more powerful than Hubbell, to look for what are called biosignatures or biomarkers in the atmospheres of planets orbiting other stars. This is all within our technological capability. And I think important, as what NASA did in the 1960s, especially in the 1970s, is we would inspire another new generation of builders and thinkers and dreamers to do all of these amazing things. And so with that, I'm going to end my talk. I'll roll credits, and I'm happy to entertain lots of questions. Okay, the mute. Oh, thank you very much.
Okay, anyone?
Please unmute yourself and ask your question.
Raise your hand.
Well, can you hear me?
I can.
Okay, good. Since first of all, I want to thank you for this absolutely spectacular presentations. It was thought-provoking, humbling, fascinating, and a totally new perspective. Thank you so much.
No, thank you.
Speaker down.
That's very sweet of you.
We went searching for zombies. If people would be
And now, Jacob, you can do your, I'll let Jacob take over with the question and answers.
Okay,
I have Chris LeBeau as the first one on my list. Chris.
raise your hand again.
Yeah, I put my question in the chat there.
Yeah, I
I'm
see.
curious, how deep are the oceans sitting beneath some of these ice crusts? And what is the most significant thing we've learned from space travel and observation?
Oh, great. So it's a double question. So thank you, Chris. So first, for the depth of the oceans, they are comparable, if not even greater than the oceans on Earth. I think one of the factoids I remember is that one of Jupiter's moons, I believe it's Europa, the one that scientists say is the best place to go look for alien life that exists right now. They've calculated that the liquid water beneath the surface, the ice crust, and that ice crust is deep, it's many miles thick. So it would take a lot of technology to land something there and drill through that, or even if we land near one of the cracks where material's coming out sometimes just to get through all that ice. But they've calculated that the water, the liquid ocean underneath that icy crust has more water than all the oceans on planet Earth. And so we're talking about depths of miles, just like the deepest oceans on Earth. Maybe tens of miles. So I have a follow question from you. So what is the most significant thing we've learned from space travel and observation? I would come back to the evidence for possibility of life out there. Like I like to tell my students, the chemicals for life are abundant in the universe. They're everywhere. The chemistry that we're made out of is very normal. We're made out of carbon and iron and oxygen, etc. These chemicals are everywhere. But what we at least know about life on Earth is the main ingredient it needs is liquid water. Liquid water is very important. So where we find places with liquid water, those are fundamental discoveries for places to go look for life. And before the Voyager missions and before this exploration of the outer solar system over the last 20, 30 years with these bigger missions, we didn't know about any liquid water. We knew that there was ice water out there everywhere, but we knew of no other places besides Earth with liquid water.
Thank you.
Sully, please
Oh.
ask your question.
Hi, I thought that was an outstanding talk. Thank you very much.
Oh, I appreciate that. Thank you.
One of the striking things is that Earth has a single moon, but many of the other planets have multiple moons and many moons. Why do you think that is?
Yeah, that's a great question. So if we break down the 8 major planets into, we have 4 rocky ones in the inner part of the solar system, only the Earth really has a real moon. Mercury does not, Venus does not, Mars has these couple captured, pebbles in orbit. And if you think of the outer 4 big planets, you got 2 gas giants and 2 ice giants, and they're huge compared to the Earth. I said, oh, Jupiter's 10 times the diameter of Earth, so it doesn't sound like very big, but in terms of mass, it's hundreds of times more massive than Earth. So it has a huge amount of gravity. And so the idea is that after the solar system and the sun formed, there was basically a big disk, kind of like the rings around Saturn of debris, lots of rocks and pebbles and boulders and protoplanets, bigger blobs. All that stuff was like a giant system, kind of like a ring system around the sun. And over time, the bigger chunks had a larger gravity. They started to gravitationally pull the smaller chunks that were close enough to them into orbit around them, as we've seen in a couple cases. And so basically the really large planets like Jupiter and Saturn just have so much gravity, they've just collected big collections of small objects around them. Uranus and Neptune are a little bit less massive, and so they have fairly big collections, just not as big as Jupiter and Saturn. And it's the same idea with the ring systems. They also have ring systems, which is more material in orbit around them. Whereas the inner solar system, these are our planets like the Earth are just tiny, tiny little rocks. They have gravity, but not strong enough to capture things. So how did we get the moon? And the moon is very unusual because the moon is so large compared to the Earth, right? It's only 1/4 the diameter of the Earth and about 1/100th of the mass. And so basically you can take 100 moons and pack them into the Earth's and have the same weight on your scale. The best theories about the formation of the moon is that during the early solar system, where there's this big ring of debris around the sun, that things were colliding into each other. So lots of collisions and things are crashing into each other. And every once in a while, fairly large objects, like we believe something about the size of Mars, hit what we call proto-Earth, which was slightly bigger than it is now, and hit it in a kind of a grazing, if I get a softball here. So if this is the proto-Earth, hit it kind of in a grazing angle. And so if it would have hit it straight on, like a head-on impact, it would just broke Earth apart. But it hit it at a grazing angle and kind of peeled off the outer crust of the proto-Earth, kind of like peeling off the rind of a orange or whatever. And so it pulls all that material off Earth, but not hard enough so that object collides, grazes Earth and goes off into wherever, into the solar system. And that material that got stripped off the outer crust of the proto-Earth stayed gravitationally bound to the Earth and orbit around the Earth, and over time reformed into this big ball of rock, which is the moon. And the moon basically has the composition much more like the Earth's crust than the Earth itself. It doesn't have much of a dense metallic or iron core, a little bit, but not much. It's mainly made out of the same material as the Earth's crust. So that's how we got the weird situation where you have the Earth with one big moon. That's what we believe. That's our theory.
Okay, thank you.
Bill, Eddie, your turn.
I pass. I'm
I have a-
fascinated with the, oh, Linda has a question.
Yes, killer asteroids.
Or what are asteroids?
Killer asteroids.
Killer asteroids, yes. Yes, killer asteroids exist, and we should be worried about them. So killer asteroids, so again, we have this, I got to step back a little bit. We have the solar system, the Earth, the sun forms, it leaves this big ring of material right after the formation of the sun, which the planets form
Can you
out of.
please take this with you?
And it just turned out that the space between Mars and Jupiter, all that material in there was no big objects around. And so that material basically got left behind. And so the asteroids that are sitting between the orbit of Mars and Jupiter, there's several million at least. They're all orbiting the sun in the same direction as the planets. They're all orbiting in the same plane. So they're part of that leftover disk, mostly rock and ice, some metallic. They're happy in their orbit, undisturbed, going around the sun for billions of years, just like the Earth, just like Mars, just like Jupiter. Now, what happens though, is if something comes along, like an object from outside the solar system or an object from the outer part of the solar system gets deflected by gravity and sent towards the inner solar system, if it goes by some of these objects, it could perturb their orbits gravitationally, change their orbits, change their trajectory, and they could wind up having a crash course, a trajectory heading for Earth. And if they collide with Earth, they can cause a lot of damage. We know that all the objects in the solar system get impacted by large and small objects all the time. We see craters in every single object we look at. We see craters on the Earth. We know from looking at the craters that this happened a lot more in the early history of the solar system and has died down in terms of the frequency, but still just 65 million years ago, which is a tiny fraction of the time between then and 4.5 billion years ago. So 65 million years ago, we got hit with a pretty small object, an object smaller than one of Mars's little tiny asteroid moons. That little object, about 10 miles in diameter, hit the Earth with such force that it wiped out 99% of all living things on the planet. That was the death of the dinosaurs, and about 90% of all species of life on Earth were made extinct from one 10-mile diameter impact. So that's why we call them killer asteroids, or killer comets are probably more likely to be the danger, because there's far more comets. There's far more big comets. So there's lots of comets that are tens and hundreds of miles across. And I mean millions of these objects. They're out way past Neptune. So every once in a while, their orbits can be disturbed as our whole system passes by other star systems several light years away. And we believe, so it's not an if we'll get hit again, it's a when we will get hit again. And we have dedicated missions and telescopes that are called Space Watch that are constantly keeping an inventory of objects out there that could potentially hit us. So maybe we could do something about it if we know about it early enough.
Thank you.
Okay.
So, yes. We don't need that.
Norton or Irene, what's your question for Daniel? You have a question for Daniel, Norton or Irene Starr?
Not I.
Okay. Stephen Drever, welcome
Hi.
back.
Okay, hi, Danny. Thank you very much for your great presentation. It was wonderful. I have a question about the budget for research and basic research. It's pretty low, as you pointed out. Do you happen to know if there's any plans in the new administration that's going to start January 20th to increase budget for institutions like NASA and science research?
Yeah, that's a great question. I don't know. I mean, of course, I've heard Biden is has a positive forward-looking statements about science, and so that gives me some hope that there will be. It's been a slow decline over the last 30 and 40 years as presidents from both parties have been in charge, and the House and the Senate has been run by either party. It always, even though it's such a drop in the bucket, again, 2 pennies of every single tax dollar that we give Uncle Sam, it always comes down to this big fight about non-discretionary spending. Non-discretionary? Yeah.
Right.
Thank you. And it's always frustrating to me too, because the impact on the economy I just talked about the impact on the economy in terms of new technologies and so forth, and hiring all these people, and how it impacts every single state gets their economy gets boosted from scientific institutions. It's not just NASA, it's all of it. So it's a huge, as economists have done studies that shows for every dollar invested in federally funded basic research and development winds up paying off dividends of something like $10 in the future, but it's a sort of long-term forward-looking investment. And I feel like our political systems in the last 2 to 4 decades has become very short-term. There's a lot of short-term sort of thinking. So I don't know of any plans at this point. I'm sure at some point Biden will have a budget. And, as Obama did, there was some increases for agencies like NASA. To be fair, the Trump administration did not cut NASA funding. Actually, they either kept NASA at static funding, or even gave it a little bit, few percent increase, though there were a lot of other federal scientific agencies that were not supported in the same way. But it's a big political thing. So I guess I'll be biased and say that when I give these talks, I explain and want to give this one sort of key takeaway about how much we spend and what the benefits are for such a small investment, that I'm hoping that people out there in the audience will feel inclined to write and call their representatives and just say, look, this is important to invest in it, just up it a little bit because it's such a small amount. But it is very political. I mean, we make choices and we decide either to invest more or less.
Okay, thank you.
That's as political as I'm going to get.
YM,
Yes.
it's your turn.
Well, Dan, first I want to congratulate you for such a wonderful talk. I'm in the same department as yours, but my area is condensed matter physics and biophysics. So I have one question. Where is the intersection between the biology and the astrophysics?
Oh, that's a great question. Between biology. Yeah, that's a great question. And there's actually a big connection. So in the last 10 or so years, a whole new scientific enterprise has started, not just in the US, but across the world. It's called astrobiology. And it is.
Yes, I heard about that, yeah.
Yep. And there's an astrobiology institute, a NASA institute, and there are several universities that have graduate programs. For instance, Arizona State University has a graduate program in bioastrophysics. And the reason being is, again, we know that the chemistry for life is out there, and especially in the inner solar system. So there's basically 2 places that we can think about looking for and studying life. And this is what the astrobiologists do. So I said astrobiology. One is these interesting worlds in our solar system. So Mars and these icy moons that we know have salty liquid oceans under their surface. So nearby planetary science, solar system exploration, that's one area. And that's led to a whole branch of studying weird life forms on Earth, which are called extremophiles. And so there are types of life on Earth that live in very toxic conditions that would be completely deadly to people. So for instance, near the deep sea heated vents where the temperature is like the temperature of boiling water and all kinds of toxic gases are coming out of the seafloor vents, there's all kinds of life living right there. There's these weird small organisms, microscopic organisms that live in some really acidic and alkaline lakes around the planet. And so they studied those kind of objects, these kind of life forms on Earth, trying to decide how we could look for their signatures in the inner solar system, or not the inner solar system, in the solar system. And then besides the solar system, we also now know in the last 20 years that basically planets around stars are ubiquitous. They're everywhere. Like when you make a star, you make planets, just like you did here. Every single star we look at, we now know that there's planets orbiting around them. And we've done this by giant statistical studies. A way I like to conceptualize is if you go out and look at the sky and it's clear, every 5 stars you can see, one of those 5 stars has a planet probably like Earth in orbit around it. And what I mean by that is a small, rocky, dense planet in orbit in something that's called the Goldilocks zone or the habitable zone. So in orbit, not too close to the star where it would be too hot to have liquid water, and not too far from the star where it'd be too cold to have liquid water. So that doesn't mean it has liquid water. Like in the solar system, Mars is in the habitable zone, but it doesn't really, it's too cold. Maybe every once in a while, a little water comes out, but it's too cold and the atmosphere is too thin and toxic. But looking with telescopes at those distant worlds and trying to dissect with spectroscopy what's in its atmosphere that would give a clue that there's life on the surface. So for instance, if you look at a planet and you can dissect its atmosphere and you see a lot of oxygen like we have in our atmosphere, that's a good indication that there's life on that planet. And so that's why there's a whole new branch of astrobiology. And
Thank
it's
you.
a very, very active field.
Yeah, thank you.
Okay, with all those questions apparently answered, because there's no one more that has unmuted themselves, I want to thank Daniel.
Sully has a question.
Okay, who?
Sully.
I can see everybody this way.
Hi.
Yes. Sully, go ahead.
Yeah, this is possibly an unfair question because it's not on the direct topic that you
I
talked
like
about.
those too.
I see that you spent some time at UCLA, and one of the recent Nobel Prize winners is on the faculty there. So
yep.
The understanding I have is that she got the Nobel Prize for discovering that at the center of our galaxy, there's a black hole. So can you comment on that, the implications of it, and also how do you detect a black hole?
Oh, great question. So yeah, this is a really cool story. So Andrea Ghez is my age, and I actually was an acquaintance of hers. I can't say I'm a friend, but when I was leaving UCLA, graduating and heading off to Arizona, the last couple months, the end of that spring quarter, and probably into the summer, because I was still working on some research, she was coming in as new faculty, and she was coming in as a postdoc from Arizona. And so I was talking to her all the time about what is Arizona like, and she was actually very cool. And then when it turned out, shortly after she started at UCLA, her and her colleagues had it's actually a very simple idea, but it's a very smart idea, which is UCLA is part of the system of University of California universities in partnership with Caltech that run the Keck telescopes on Hawaii. There's 2 of the biggest telescopes in the world, the Keck 1 and Keck 2, and they have, they're not public telescopes. They're only dedicated to those institutions. And so they have this great resource, and they have infrared cameras, so cameras that look at light wavelengths a little bit redder than we see with our eyes, that allow us to peer down towards the center of the Milky Way in the constellation Sagittarius and see through all the kind of gas and dust clouds, which actually form into stars, peer through all that stuff to look at the heart of the galaxy. And they knew at the time, astronomers did, and this is in the late 1990s, when she started this experiment, that there's a big cluster of young stars at the center of the Milky Way galaxy. They knew that. And so they just basically wanted to use the biggest telescope with the best cameras to look at that region, kind of about a few light years across region, and look at these couple hundred massive stars all in this young cluster that are all kind of swirling around each other. And what they realized in the next couple of years, they just basically go back there every couple months to the telescope, take some snapshots, and they start to piece together a movie of all these stars at the center of the galaxy. And they realize after about 5 or 6 years that the stars are all moving, and they're all moving in elliptical orbits, just like Kepler's laws, just like why the moon goes around the earth and the earth goes around the sun. They were doing exactly that same motion. And when you see them orbiting, you can calculate how fast they're orbiting. You can see where the focus of their orbit is, what's at the one of the foci of the ellipse. And the interesting thing they realize, especially this one star that's already completed more than one orbit in the last 15 years, moving very fast, it's orbiting nothing. There's nothing visible at the place where the object that it's orbiting is. And there is a source of extreme radiation from that place that you can only see in radio wavelengths, like the big radio dishes. And so they put that together with the fact that this thing's orbiting this tight little spot, and they had a suspicion that there was a big black hole there. That experiment of tracking the orbits of the inner stars gave us a precise measurement of the mass causing that star to orbit. And the mass, the amount of material that you need to cause gravity to create that star in its orbit, is about 4 million times the mass of the sun, yet you don't see anything. And so basically from those measurements, they know it's something that massive and not visible and denser than any known matter that we know of, which are neutron stars. So we had other suspicions about black holes over the last 30 or 40 years, but that observation is probably one of the best observations for what I would say, it's not proof that there's black holes, but there's proof that there's something very massive, very dense, and doesn't emit light. And we don't know of anything else that it could be besides black holes. And so it gives very strong piece of supporting evidence for the existence of black holes.
Okay.
I don't know if I answered your whole question. I get carried away. So if I didn't.
Okay. Robert Groene, you are the one with
That's
the question.
me. Yeah, this wonderful talk, Dan.
Thank you.
My basic question is, was Carl Sagan too optimistic? I'm thinking about intelligent life forms. I mean, we've been listening through the skies. We put a gold record with my idol Chuck Berry on it, sent out, and all of this, and nothing's come back, right?
That's true. So was he too optimistic to think that there was life out in the universe is the question?
Yeah.
Yeah, that's a fair question. And there's a famous physicist in the 1950s named Enrico Fermi had something called the Fermi paradox, which he basically said a similar question as yours, Robert, which is, with all the stars out there, if there's planets around the stars, we didn't know about planets, but just let's assume that there's nothing special about the solar system other than we live here. You do the math and you think, wow, there should be lots of signals if there's, so much life. If you just think about even if there's life on lots of planets, but very few get to the point of evolving to intelligent life like us and starting to communicate, you might expect to see signals. And so this led to a big question. The question still exists. People think about it in different ways. I mean, first of all, the volume of space that the Milky Way galaxy, which is just one galaxy out of billions of galaxies in the universe, like the average distance between stars in our galaxy is huge. And so just to give a perspective, we've been broadcasting radio and TV signals away from Earth just on accident, just because we broadcast radio and TV signals, right, and they permeate out into space, going in all directions away from us like this. So that's about 100 years now. So if you go out 100 light years in any direction from the Earth, that's where signals have reached.
Okay.
That only encompasses a few thousand stars, and the Milky Way galaxy contains a few 100 billion stars. And so there might be totally intelligent life broadcasting things at the speed of light on the other side of the galaxy or 1,000 light years away. We're not going to know for a long time because of these great distances. And so you could even have civilizations come and go, and it would be a long time before we saw any evidence.
Yeah.
I'm going to come back to the Voyager record because I love that story. The other sort of less positive thought is that yes, life is ubiquitous like the planets are. This is a hypothesis. But when you get to the point of intelligence, you get so smart as a civilization that you wind up killing yourself. And, you know, we have created mass destruction weapons. We're now messing with the climate of the planet. We could run out of resource. You could see lots of scenarios that are intelligent caused, possibly.
Lots of sci-fi books on that. Yep.
Oh yeah. And then there's also the, you know, accidental collision with something, you know, like a 20-mile diameter comet that wipes out everything on the planet. That could happen. As far as the Voyager records, it's true. Sagan put on, I love the story. We could do a whole talk on that. These 2 golden records, and on the records, they have all kinds of pictures and music and welcomes from, I think, like welcome messages from something like 150 of the languages of humans. And on the album, there's like a diagram that he figured that if you're smart enough alien that captured the Voyager spacecraft, you could decipher this diagram on the album, and it would basically tell you where Earth was and told you about Earth and people and things about hydrogen, basically enough clues that a very smart puzzle solver would be able to figure out where we come from and how to play the record, how to create a machine to play the record.
Right.
The problem is Voyager now, and Voyager 1 and Voyager 2 that have the golden records on them, they've been on their journey now for over 40 years, going something like 50,000 miles an hour. They're not even a light day away. So the nearest star besides the sun, which is 8 light minutes away, is 4 light years away. And they're only 1 light day away. So they're like 20,000 years away from passing a nearby star. Well, some astronomers have recently calculated which stars they might pass by. But even if they go right through a solar system that's teeming with life and technology and civilization, the space between the planets is very big, and the chance of seeing this little tiny thing go by, especially, you know, tens of thousands of years from now, when all of it is turned off because its nuclear battery is going to run out of fuel pretty soon. It would be pretty, you know, it's a real needle in a haystack sort of situation to find that record, even though it's a neat idea.
Okay, thanks, Dan.
Okay, Greg Johnson, you have a question?
Yes, sir. Really enjoyed your presentation, Doctor. I took astronomy in college and physics, and I loved both those classes, and I really strongly respect your what you do and what you teach at UMKC. So I want to applaud you for all that you do for the university and the students. But I have a theory, and the question is on my theory. And I wanted to see if anybody else had actually asked you this before, that you take the diameter of Earth, and you take the diameter of the sun, and you take the diameter of the moon, and all 3 of those objects are orbiting each other. Mm-hmm. And the distance, the Earth from the moon, and the distance from the Earth to the sun, when all those become in orbit, you get a lunar eclipse or a solar eclipse. Yep. That's a fairly unusual phenomenon. And my theory is, it's a theory, Greg Johnson, that there has to be a stronger, a greater being out there that created that those phenomenons that could occur to have a lunar eclipse and a solar eclipse. And I just think there's some supreme being out there that made that happen. That's just coming from me.
Okay, so it is true that you know, the moon is tiny compared to the sun. It just happens to be, I would say, a coincidence that you have the size such that when the moon is between the Earth and the sun, at sometimes, not all the time, its disk on the sky basically is exactly identical in size to the disk of the sun. And to give it a human perspective, if you go out at night and you look at the moon, you hold your hand out at arm's length, the size that the moon is on the sky is about the size of your pinky nail at arm's length. It's smaller than like a dime if you hold a dime up at arm's length. We think it's a lot bigger when we see it, but it's tiny, tiny. And that disk is, you know, at certain times in the moon's elliptical orbit around the Earth, it's just right. So when it covers the sun, you get a perfect solar eclipse. The lunar eclipse actually is easier to happen. It doesn't have to be, it's the size thing doesn't matter so much, because you also get the conditions for a solar eclipse. Everything has to be just right, and that thing only lasts for a couple of minutes. We have lunar eclipses every year, maybe twice a year, and you can see a lunar eclipse over on Earth. Sometimes the moon's a little bit too close, and so you get what's called an annular eclipse. So you see the sun as a ring rather than the beautiful solar eclipse. The truth is, in any orbiting system, you're going to have objects in between you and another object and get some sort of an eclipse. That's actually how we know about all these planets orbiting other stars, is we look in the direction of those planets with our telescopes. And if the orbits of the planets, they're all orbited randomly, but the some that are orbited with the planet plane, orbital plane in the line of sight, the little planet passes in front of the star and makes a little tiny eclipse. It doesn't block all the light out, it blocks like a tiny fraction of the light. And we can measure that as a dip in the brightness of the star. And if it repeats every 2 years, we're like, oh, there's an object that's orbiting every 2 years. So the fact that you have so many objects doing all orbits around each other, you're always going to have the case where something gets between something else sometimes. You're going to have these special eclipses where either all or some of the light gets blocked out. The fact that it works out that the moon is just so at this time, because it also is changing over time. The moon is slowly moving farther away from the Earth. So I forget what it is. It's like a couple inches a year or something like that, or a couple inches every 100 years. It's slowly in its orbit is kind of spiraling outwards. And so even that condition is going to go away, that in, I don't know, millions of years in the future, according to our calculations, there won't even be the beautiful solar eclipses like we see now. So that's what I have to say.
Thank you.
Okay, YM, you're
Yes.
probably the last one. Ask your question.
We can't see.
I already asked them my
It
question.
changes.
Okay, if no more questions, please unmute yourself if you do have questions so I can see you. John Killip, John or Caddy?
Go ahead, Kevin.
Okay, my question is, what is your thought about private enterprise entering the space exploration?
I think that's a good idea. I think it's going to happen because, for instance, the asteroid belt, which I described, which isn't too far away from us, and every once in a while, Earth-crossing asteroids, meaning asteroids that got disturbed in their orbit, pass through the inner part of the solar system and pass fairly close to Earth, so they wouldn't be so hard to get to. They wouldn't be so expensive to send rockets and spacecraft to land on. Some of these objects are super rich in all kinds of materials, like different kinds of metals that we use for computers, platinum, and so forth and so on. So much so that the economy, the cost of sending the spacecraft there, landing, using robots to drill up stuff, collect it, and bring it back, even though that would be very expensive, might actually beat the cost of trying to extract those resources from Earth. And so I think that will definitely drive private enterprise. Some space tourism is going to drive private enterprise. But I would also argue that private enterprise never has the amount of capital, even of some of our large corporations, and the sort of investment horizon to do like a long-term investment that's going to pay off dividends in 10, 20, 30 years compared to a federal government, whether it's the US or other governments across the world. For instance, there's the European Space Agency, which is NASA's counterpart from the European Union. Corporations are never going to spend huge amounts of money in basic research and development with the timeline for getting profit from that investment of more than a couple of years. So they will get involved when there's a profit margin, but it'll be in terms of resource extraction in nearby. It won't be in terms of exploring things out there. You still need your basic research. I mean, 100 years ago, we were doing basic research on things like radioactivity and electrons, just for the simple sake of being, a nerdy scientist and saying, wow, what is this? I don't understand. I want to understand it. No practical application. 100 years later, we all have cell phones, right? And that early 100 years ago basic research has turned into who knows how many trillions of dollars in terms of economic output, but the time horizon for it is so great. So you need both, I would argue.
Thank you.
Okay. Then it looks like I have no more questions for you. So it's at me the honor to thank you so very much for your very clear and entertaining presentation. You really made this a very special event for us. And to anyone that had some problems with the earlier part of the session, where we tried to make tables that allowed conversation among people, let's hope that we'll learn from this and we'll do it even better next time. Anyone that wants to stay around, please do so.
Yeah, I'm
I
happy
will
to
not
entertain
end the
a few more.
session. Yeah.
Thank you, Daniel, so much. Thank
Oh,
you.
thank you all. I appreciate all the
Yeah.
questions. A lot of fun.
It was a lot of fun, and thank you all for participating. And don't forget that we need some action pictures, backgrounds, space helmets that we saw flipping by, the Killips. We need some pictures to illustrate this in the beacon. So please, or if you want to write comments or something like that, we'll be happy to take that as well.
Bibi, I will say I just took a screenshot of the whole the gallery of all your pretty faces. So I'll
Oh,
send it to you.
wonderful, wonderful. Send pictures to Jacob, since
Okay.
the pictures will be, he will post them on our website. And then I can see them all and I will pick. And of course, Dan, there will be a picture of you appearing in the beacon and a few others. So please help out to make the next beacon interesting and stimulating, because this is the format that we will have to use for, yeah, I figured quite a long time. And even when we can get back into our lovely suite at the library, we probably will want to reach out to people who are not able to come to the rooms. So I think that would be nice, wouldn't it?
Yes.
Yeah.
Bravo.
So that we
Okay.
can reach out to everybody. Jacob, I'll shut up.
An update. This week, they're actually going to do the breaking work to start our audiovisual upgrade. So Linda has been warned for when she's there that they're going to work it. And in a couple of weeks, we should have our updated suite, which will have the capability of have a live speaker and at the same time for everyone out of the area, a recording or a live Zoom participation.
That's great.
So that's an important part that we wanted to realize. Thank
thank
you
you,
all. Thank you all participants for making this a very special evening, which lasted almost 2.5 hours.
Wow. Yeah.
So no moment was wasted and was very enjoyable.